we can rehash one last formula for parameterizations. We had a formula for the length of a curve, which we derived using Riemann sums earlier in the course. Now if we have parametric equations for a curve, x equals f of t, y equals g of t, we can do the same thing. We can take the limit of a Riemann sum to find the length of the curve, and the computation is very similar. We get the length of the curve from t equals alpha to t equals beta is the integral from alpha to beta of the square root of dx dt squared plus dy dt squared with respect to t. And we're assuming here that our curve is traversed exactly once as t increases from alpha to beta. And of course this is the integral from alpha to beta of the square root of x prime t squared plus y prime t squared dt. If, as before, our curve is the form y is some function of x, remember our formula was that the length as x varies from a to b is the integral from a to b of the square root of 1 plus dy dx squared. And now you could use reverse substitution, let x equals f of t, solve for dx, and we know dy dx is dy dt over dx dt, so we get the same formula here by a change of variable. Well, let's apply it. Let's suppose I want to find the arc length of the spiral defined by x equals e to the t cosine t, y equals e to the t sine t. So we see as t increases, the angle here moves from 0 to 2 pi if we interpret t as the angle, but the distance from the origin increases because this is equal to e to the t. Well, x prime t equals e to the t cosine t minus e to the t sine t, and y prime t is e to the t sine t plus e to the t cosine t. And for the length of this segment of this spiral, we have from our formula, it's the integral from 0 to 2 pi, as t increases from 0 to 2 pi, of the square root of e to the 2t times cosine t minus sine t squared plus e to the 2t times sine t plus cosine t squared dt. And now expanding the cosine t minus sine t squared and sine t plus cosine t squared, we get that this is the integral from 0 to 2 pi of e to the t times the square root of cosine squared plus sine squared plus sine squared plus cosine squared minus 2 times cosine t sine t plus 2 times sine t cosine t. And after cancelling those middle terms and noting that sine squared plus cosine squared is equal to 1, we get that this is the integral from 0 to 2 pi of e to the t times the square root of 2. And of course this is the square root of 2 times e to the t evaluated between 0 and 2 pi. So our answer is the square root of 2 times e to the 2 pi minus 1. And this is the length of this segment of the spiral defined by these parametric equations. Let's try another one. We'd like to find the arc length of the circle defined by x equals cosine 2t, y equals sine 2t, as t runs from 0 to 2 pi. Now you might think carefully about this. We've drawn this curve before, but remember this traces out the circle twice. So if we apply our formula, we have the integral from alpha to beta of the square root of dx dt squared plus dy dt squared. And this is the integral from 0 to 2 pi of 4 times sine squared 2t plus 4 times cosine squared 2t. And of course this is just the integral from 0 to 2 pi of the square root of 4, which is 2 times the integral from 0 to 2 pi of 1 dt. This turns out to be 4 pi. So the problem here is that the parametric curve traces out the unit circle twice, so we loop around that circle twice, and our equation for the length of the curve gives us twice the circumference of the circle. So it's not actually the length of the physical curve itself, it's twice the length of the curve traced out by these equations.